Good morning everyone. Let us start for the theory of computation, unit 1, second video. So I am Dr. Ezhumalai, Professor and Head, Department of Computer Engineering, RMDEC College. Let us see that some important concept in unit 1. So all of you know that there are 4 types of grammars are there accepting 4 finite automata. Hierarchy wise, let us see that the basic common grammar is called a regular grammar. It's the least powerful grammar which is accepted by finite automata. The next superior grammar is called context-free grammar. This grammar and language, context-free language, is accepted by push-down automata. The next superior language is called context-free, context-sensitive language. The language was accepted by LBA, which is called linear bounded automata. The final and superior grammar, which is called recursive enumerable language, so which is accepted by finite automata, which is called Turing machine. The complex also improved by first to last. Powerful also improved first to last. The Turing machine is modern day equal to modern day digital computer. So our syllabus, therefore there are finite automata, there are 4 grammars, 4 finite automata is there. According to hierarchy, first least one is a finite automata, the next one is a push-down automata, the next higher superior model is called linear bounded automata. The most powerful finite automata is called as a Turing machine. Let us see that. Now, the epsilon non-deterministic finite automata. What is the epsilon non-deterministic finite automata? Previously, we discussed about finite automata as 2 types. One is called deterministic finite automata. Another one is called non-deterministic finite automata. So again, non-deterministic finite automata has been 2 types: epsilon finite automata without epsilon finite non-deterministic finite automata. So definitions are common for all the finite automatas. So finite automata, epsilon NFA is quantifiable for 5 tuples, which is called Q, summation, delta, Q0 is the starting state, F is the final state. Similarly, for like a previous example, so Q is a set of states. How many states are there? The finite automata is represented by the Q, capital Q. Summation is the input of the bit. How many input of the bits are we are giving for this type, this finite automata summation? This contains represented by the summation. Epsilon is a never a input symbol, so it's not actual input symbol. So without input symbol, we can move, we can transmit one state to another state, which is called epsilon. So epsilon is defined by the without any actual input symbol, without empty actual input, we can move empty move. This is called epsilon move. So that is allowed in for the epsilon NFA. Another one is called the transmission. So transmission is called Q, is a set of states mapping with actual input is a summation with epsilon. But epsilon is allowed in epsilon NFA. So actual input is represented by Q. Q is a transition function for some other new state. One goes to another state. So Q0 initially, as like the previous example we have to mention, here is the Q0 is the initial state of the finite automata. F is a set of final state. More than one final states allowed in the both NFA and DFA. This is a formal definition of epsilon NFA. The actual example for epsilon NFA. So wherever the actual input is there, this is a starting state. The Q0 is the starting state. There are 3 states in the NFA: Q0, Q1, and Q2. So along with the actual input, 0 and 1 is the actual input. Along with the actual input, the epsilon edges also allowed. So without giving any actual input, the epsilon input can move Q0 to Q1. So this is called epsilon NFA. So but in DFA, epsilon is not allowed. Actually, NFA is only allowed for epsilon edge. So what does it mean? Without any actual input symbol 0 and 1, we can transmit one state to another state. That is use of epsilon input. This length is 0. It's not actual input. Without any actual input, empty movement one state to another state, that is called epsilon NFA. Another one is called Epsilon Closure. So epsilon means represent state can go other state without any input. This can happen only in the different happen only if the present state have epsilon transition to other state. Okay. Epsilon closure is finding all the states which can reach from the present state on one or more epsilon transition. Let us see the epsilon closure of 0. Here the 3 states are there: 0, 1 and 2. So epsilon edge is also there along with input A. here is the B, here is the C input is there. So without actual input, we can move one state to another state. 0 to 1 we can move without an actual input. That's called epsilon EPS. So 1 to 2 without an actual input, we can move, transmit 1 to another is called Q1, 1 to Q2. So with the epsilon edge. So what is the epsilon closure? Epsilon closure is nothing but a collection of all the edges which are transmitting one state to another state with the epsilon edge until reaching the final state. So like that, epsilon closure of 0 is 0. Epsilon closure at 0, by default 0 will be included in the epsilon closure. So wherever what are the edges are moving, epsilon edges are moving from 0 to other state. This edge is moving 0 to 1. So 0 to 1. So the 1 will be added here. From 1, whatever any other epsilon edges are moving from, so 1 to 2. Is there one more epsilon edge is there? So the 2 also will be added. So epsilon closure of 0 is 0, 1 to 2. The 1 by default will be added. 0 is by default added. 0 to 1, 1 will be added. 1 to 2, 2 will be added. So epsilon closure of 0 is 0, 1 and 2. Similarly, epsilon closure of 1. Epsilon, any state you want to find out epsilon closure means by default the state will be added. Epsilon closure of 1 is 1 will be added. From the 1, is there any epsilon edge moving this state to other state? So yes, 2 is this edge is moving 1 to 2. So the 2 will be added. So epsilon closure of 1 is 1 and 2. Similarly, epsilon closure of 2, there is no any epsilon edges are moving from the state 2. So by default, the corresponding state will be called as epsilon closure. So this is the method for finding epsilon closure 0, 1 and 2. Epsilon closure of the state. For example, you need to find epsilon closure of A. A is by default added epsilon closure. From A, is there how many epsilon edges are going to this to final state? So this is going to F1. F1 also will be added for the A closure. A default A will be there, along with F1 also will be added. From here, one more epsilon is going for F2. So F2 also will be added. From F2, one more edges are going to F3. So F3 also added. So epsilon closure of A means A, F1, F2, F3. So all these states are epsilon closure of A. This is the method for finding epsilon closure of any finite automata. So similarly, one more example is represented here. 3 states are there: 0, 1, 2, 3, 4. Totally 3 plus 2, 5 states are there. So in these 5 states, how to find out the epsilon closure of? Epsilon closure of 0. 0 will be added. From here you have to check how many epsilon edges are going this state to other state. Here is one epsilon edges going 0 to 2. So 2 will be added. 0 and 2 will be epsilon closure of 0. Similarly 1. From 1 there is no any epsilon edges going to other state. So by default 1 will be epsilon closure. Similarly 2. 2 will be included by default. From here, is there any epsilon edges are moving to this state to another state? So this is a 4. 2 and 4 is the epsilon closure of 2. Similarly 3. From 3 there is no epsilon edges are moving from this state 3. So 3 will be default added for epsilon closure of 3. 4. Here also no more epsilon edges are leaving from this state to some other state. By default 4 will be added for epsilon closure. This is a method for finding epsilon closures. Similarly, so what is the relation between the regular language, regular expression and finite automata? So the finite automata has two types of finite automata. One is called deterministic, another one is called non-deterministic. So non-deterministic finite automata having other two types: non-deterministic finite automata and epsilon non-deterministic finite, epsilon edge non-deterministic finite automata. So similarly, what is the relation between all the things? So regular expression, if any regular expression is given, we can convert to epsilon NFA. Epsilon NFA. If epsilon NFA is there, we can convert to DFA. If DFA is there, we can convert to epsilon NFA. Similarly, DFA we can convert to NFA. NFA we can convert to DFA. So another DFA we can similarly DFA we can convert to regular expression. Similarly, these are all interlinks. Regular expressions to NFA, epsilon NFA, NFA epsilon NFA to DFA, DFA to epsilon NFA. Similarly, DFA to NFA, NFA to DFA, again DFA to regular expression. So all are interlinked. This is the relation between, we can convert one to another. These are interlinked between regular expression and finite automata. So what is the language accepted by finite automata? So we can simply called regular expression. Regular expression is nothing but regular language. So now we can see on one example how we are going to convert NFA to DFA. So these are the procedure to follow for conversion for subset construction method to convert to NFA to DFA. The first step, create a state table for the given NFA. State table you have to create. Another one, create a blank state table under the possible all inputs for the equivalent DFA. Okay. So what we are going to convert to DFA for all the inputs, how many inputs for the NFA, all the inputs we are converted to state table. Then mark the start table of the starting state of the DFA by Q0, same as the NFA. So what is the starting state of the DFA? Is the starting state of NFA. What is the starting state of NFA? Starting state of the DFA. Similarly, starting state is common for both NFA as well as DFA. Another one, find out the combination of the states. Suppose in the NFA, there are n number of states, Q0 to Qn. N number of states are there for each possible input alphabet. You have to find out all the states for all the corresponding inputs. Next step is, for each time we generate a new DFA state under the input alphabet columns. So NFA, one state, one input. Similarly, you have to check for all the states, for all the corresponding inputs. You have to apply for the step 4 again and again until you go for the step 6. The state which contains any of the final state of the NFA or the final state of the equivalent to DFA. So what is the final state of NFA? Is also final state of the DFA. This is the procedure. Let us see the actual example. So this is the NFA. There are 3 states are there, Q0, Q1 and Q2. 2 corresponding inputs are there, 0 and 1. So here 0, first input goes to Q0. The same input 0 goes to Q1. So there is a characteristic for the NFA. The same input symbol goes to more than one state. NFA DFA is not like that. One input, only one corresponding. One input, one output. 1-to-1 correspondence. But in the NFA, the same input 0, 2 places are going from the Q0 to Q0 one input, another Q0 to Q1 another input. Similarly, this is called NFA. It contains 0 and 1 input. So 3 corresponding states are there. This is a state diagram. This is a state table. So here they see that here phi, if empty state is a common for all. Q0 is the starting state. The arrow mark which is mentioned, the arrow mark is the starting state of the NFA. So if you are giving 0 input, it goes to, one input goes to Q0. Another input goes to Q1. So Q0, if you are giving Q0 0, it goes to 2 states. One is the Q0 and another one is the Q1. Similarly, the state Q0, if you are giving input 1, it goes to Q0. That is mentioned here. So from the Q1, first state is closed for this both input 0 and 1. If you are going for second state Q1, you are giving input 0. There is no any edge transmitting from this state for including 0. No outgoing edges for the Q0 0, Q1 0. So it is empty. So from the Q1, the input is 1 means it goes to Q2. So this is mentioned here. From the Q2, no more edges are leaving from the either 0 or 1. That is called null state is given here. So this is a transition table for this given diagram. Now we have to convert to going for subset construction method. There are 3 states are there, 2 power 3. So totally 8 subset constructions possible. 2 power 3, 8 subset. First one is the phi, null set. So 0 is null and 1 also null. The second one, so Q0 is possible. 3 states are there. Q0, how many subset possible? Q0, Q1, Q2, Q0, Q1, Q0, Q2, Q0, Q1 and Q2. All 3 possibles are found. Or similarly, the phi is the 0, here phi null, 1 also null. From the Q0, so from you are giving Q0 input 0, the 2 edges are going for the DNFA. One is goes for Q0, another one goes for Q1. Similarly, Q0 0 in NFA goes to 2 states. That is mentioned here. In the NFA, Q0 input is 1 means goes to Q0. Similarly, Q1, the NFA, we are giving 0. There is no transmission from the Q1 0. From Q1 1, there is one edge is going from Q1 to Q2 for the input is 1. Similarly, Q2, no more edges are leaving from the Q2. So null is given here. From the Q0 and the Q1, 2 states are corresponding here. First we apply for Q0 0, union Q1 0. Similar result you have to mention here. Q0 0, 0 and Q0 and Q1. Q1 0. Q1 0 means only goes for the Q1. So union of these two come in as a Q0 Q1. Similarly, Q0 Q1 input is 1. Is going for union of Q0 and Q2. Similarly, Q0 Q2. Other So Q0 0, Union Q2 0.